Hi, this is Dr. Marshall, um, and this is the first video in the second part of the Chemistry 1-3 Compounds, Basic Compound Structure Nomenclature discussion. We've already talked about the basic compound structure for both ionic compounds and covalent compounds and how we get those. Next, we need to talk about how we're going to come up with the formulas, the chemical formulas for these compounds, as well as their chemical names. And we're going to start by talking in a little bit more detail about ionic compounds. So if we go back and solidify some thoughts here, if we take out a periodic table, and I've shown them images of them, what I want you to see in the lesson below as well, but you could also click here, and that'll take you to a separate image of a periodic table. Excuse me. And you can click back and forth between that and the lesson here. So I'm going to open that up again and then jump back to the lesson here. So I've got my periodic table here, and you should see that between element 5 right here and element 13 right here, boron and aluminum, there's a zigzag line running down and to the right, so where my highlighter is, and this separates the elements into the left 2/3 of the periodic table and the right 1/3 of the periodic table. And for now, we're simply going to say that this divides the periodic table into metals and on the left and nonmetals on the right. And that's what goes in those blanks there on your worksheet. And we can say that in general, metals have most or more loosely held valence electrons. We figured out what valence electrons were in the last discussion. They have more loosely held valence electrons, and they're willing to give them up to become more stable, while nonmetals have more tightly held valence electrons, and they don't want to give them up. Okay. Now, in almost every instance, we could talk about the formation of an ionic compound involves a metal atom giving up one or more electrons to a nonmetal. So the thing that you need to, the sequence that you need to focus on as far as happening is that things on the left of the periodic table give up electrons to things on the right. So things over here give up electrons to things over here. Okay, and then the things on the left become positively charged, and the things on the right become negatively charged. If I lose electrons over here, I'm going to have more positive charge. If I gain electrons over here, I'm going to have a negative charge. Okay, and then the positive and negative things attract, and this is what forms the attraction we call an ionic bond. Okay, so that's the sequence of events. One of the things that we haven't talked about yet is how many electrons can a metal atom give up and how many can a nonmetal atom take. And so the answer depends on how many they have in their valence shell to give up in the first place if you're a metal, or how much room they have in their valence shell to take electrons if you're a nonmetal. So we've already seen how an electron is added to the valence shell as we increase the atomic number through the first 18 elements, right? In the first shell, I add 1 or 2 electrons for hydrogen and helium, and then I go to the next energy shell and I add an electron for lithium, and then 1 for beryllium, and then 1 for boron, and then 1 for carbon, and so on. Okay, and if we look at those first 3 rows again, we'll notice at the top of the columns there are some headings, and in this periodic table it's just we've got 2 different sets of headings. We've got just a numerical sequence from 1 through 18. More importantly for us, we have A columns and we have B columns. And in the A columns, or in the first 2 columns, we have 1A and 2A, as we can see there. And then in the last 6 columns, we have 3A, 4A, 5A, 6A, 7A, and 8A. Okay, and these numbers are very important to us. So the thing that you need to burn into your brain now at this point is that for the A columns, the number at the top of the column represents the number of valence electrons in that column. And understand that the makers of the periodic table didn't actually plan it this way, okay? They didn't know anything about valence electrons when they created the periodic table, okay? They didn't know that the first column elements had one valence electron in their outer shell. They didn't know that the second column elements had two valence electrons in their outer shell. They didn't know this. Nevertheless, as it worked out, the periodic table informs us about the number of valence electrons an atom can have or has by what column it's in. So all I have to do to find out how many valence electrons each element has in the A columns is just look at the number of the A column. Okay, it's as simple as that. So we're going to turn this information about valence electrons into something useful here. We're going to create a little table, as we can see down below. And we remind ourselves again, when metals from group A elements ionize to form ionic bonds, we'll say that the number of electrons the metal atom will give up will be the actual number of valence electrons it contains. So if I contain 1 electron in my valence shell, I'll give up 1 electron. If I contain 4 electrons in my valence shell, I'll give up 4 electrons. Now, because this is a loss of 1 negative charge for each electron, the positive charge will also then be the same as the number of valence electrons. So, if I'm in column 1A, I have 1 valence electron, I'll give up 1 valence electron, and I'll have a charge of +1. If I'm in column 3A, I have 3 valence electrons, and I'll give up 3 electrons, and I'll have a charge of 3+, and so on. For nonmetals, which always take electrons, we'll say that the number of electrons they'll take will be the same as the number of spaces they have available. Because each additional electron adds a negative charge, because the maximum number of valence electrons is 8, we'll say that the charge of the resulting ion will be the A column number -8. So let's complete this table that follows here, and we'll just walk through this real quickly here. So let me get to a spot where I can fill this in. Okay, so I've got this table where I can write on it now, and so let's just walk through this. If I'm in column 1A, I have 1 valence electron, right? That's what that means. I go to my periodic table, I see column 1A, I see hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, and each one of those will have 1 valence electron. So I know that means I have 1 valence electron to give up. So if I have 1 valence electron to give up, that's how many I give up. 1 valence electron. And as we've already said, that means I have a +1 charge. Okay. Now, in column 1, I don't have any nonmetals, so there aren't any elements that are going to take electrons in column 1, so I'm just going to put a dash through that. If I go to column 2A, okay, I start with beryllium, and then I have magnesium, and then I have calcium, and strontium, and then radium, or strontium and barium and then radium. And I know all of those because they're in column 2A have 2 valence electrons, right? We have 2 valence electrons. And I'm going to give up 2 valence electrons then if I ionize. That means I'm going to have a +2 charge if I ionize. Okay. And again, as in column 1A, I don't have any nonmetals, so I don't have any elements that are going to take electrons and have a negative charge. However, when I go to column 3A, okay, we're going to have both a metal and nonmetals. And remember that in column 3, if you go back and look at your periodic table, that starts with boron, and that's where the zigzag line starts. And boron does, in fact, is a nonmetal. We don't usually talk about it forming ionic bonds. It usually only forms covalent bonds. But if it did form covalent or ionic bonds, it would take 3 electrons. It would take 5 electrons. It's got 3 in its valence shell, right? And it has spaces for 5 more. So if it did, it would take 5 valence electrons. And if it took an additional 5 electrons, it would have a charge of -5. Okay? It doesn't really do that, so we're just going to cross those out. It doesn't really do that. We don't have that for boron just because of the way boron works, but we won't really talk much about that. On the other hand, in column 3, starting with aluminum and then going down from there, we have metals that have 3 valence electrons in their outer shell. If I have 3 valence electrons, I'm going to give up 3 valence electrons. I'm going to have a charge of +3. Okay? If I'm in column 4A, now I do have some elements that will participate in ionic interactions that are nonmetals. I have carbon and silicon, and if they do participate in ionic interactions, they would take 4 electrons. Okay, so I'm going to take 4 electrons because they have 4 spots, right? They have 4 valence electrons and they have 4 more spots available. And if they do that, they're going to have a -4 charge. Okay, and I also have some metals in column 4A. These are the things on the left side and below the zigzag line, and these are going to start with germanium, and that's below silicon, and then the elements on below that, they're going to have 4 valence electrons in their outer shell, so they'll give up 4 valence electrons. And if they do that, they'll have a 4+ charge. If I go to column 5, same thing. I do have some nonmetals in column 5, okay, and these are going to especially be nitrogen and phosphorus, and the nonmetal below that. And if they take electrons, since they have 5 spots in their outer shell, they're going to take 3 more to fill that outer shell, and that would give them a charge of -3. On the other hand, I have a couple of metals in column 5A. Okay, I have the metals down at the bottom of 5A. They're going to have 5 valence electrons, so they would give up 5 valence electrons. They'd have a charge of +5. Then in column 6A, I have one last metal, and that's polonium in column 6A, and it has 6 valence electrons, so it would give up 6 electrons. I'd have a charge of +6 because now I'd have 6 more protons than I do electrons. On the other hand, in column 6A, elements like oxygen and sulfur especially, they have 2 spots left in their outer shell, so they're going to take 2 electrons. That would give them a charge of -2. And then in 7A, I don't have any more metals that are going to give up electrons, so we're going to put blanks there. But if I'm a nonmetal in column 7A, which all of them are, I have 1 spot left in my valence shell to fill, and I'll take an electron and I'll have a -1 charge. Okay? Now, in column 8A, I have all of my spots filled, so I'm not either going to give up or take electrons, so I'm not going to do anything in that column. So we've got this nice little table here. I'm going to have to go to the next video, but we've completed this little table, and this should have cemented in our brain how this all works. So go to the next video, and we'll pick up from there.